Hello and good morning everyone. I welcome you all to India's largest e-learning platform and academy, and I welcome you all to our channel of Gate Conqueror. Welcome you all to my session of Antennas MCQ series. We are into part 10. This MCQ series is very important. It will be useful for all the aspirants who are preparing for competitive exams, where antennas is a syllabi. So that's the advantage that you have with this particular series. And before we start, let me introduce myself. I'm GC Reddy, having 15 plus years of experience in teaching, guiding and mentoring GATE and ESC aspirants. I work as motivational speaker, pan-India from the past 12 years, expert in field theory and communications. Before we move in, this is the link for the Telegram channel of our YouTube channel Gate Conqueror. This is the link here where you can join us on Telegram. Once you join us on Telegram, you'll get the access of all the Gate Conqueror faculties, including the legendary K.M. Rao sir. This is the link here where you can join us. And the good news for all the Gate Conqueror followers is that now we are increased in strength and we are very much determined to complete the GATE 2023 syllabus comprehensively. GATE and ESC 2023 syllabus will be completed comprehensively without any doubt now. So that's the good news for you people. We are into antennas, which is part of EMFT. In EMFT also, like we had covered comprehensively EMFT so far, and I can say that you cannot get better videos on EMFT on any other channel except an academy, Gate Conqueror. Except Gate Conqueror channel, you cannot get videos better than here on any other channel here for EMFT especially. Why I am telling this is, in EMFT we have total of 5 modules. Module 1 is elements of EMF theory. Module 1 is elements of EMF theory, which is common for electrical and ECE. This is complete syllabus for electrical and module 1 for ECE. And all those who are preparing for GATE and ESC, both can go through these videos. See, the uniqueness of my teaching is, I teach in such a way that the content will be suitable for both GATE and ESC at a time. In this also, we have done so many number of derivations, exclusive theory, previous year questions, practice questions were solved in module 1. And we have created a playlist, wonderful playlist with 40 videos and 50 hours of recording. With 40 videos and 50 hours of recording here. Some wonderful videos here in module 1. Module 2 is EM wave propagation. Module 2 is EM wave propagation. In this EM wave propagation, we will discuss how EM wave propagates through free space, through materials where there is finite conductivity, through good conductors, through good dielectrics, and through perfect dielectrics. on this. Also, we will create a playlist. 10 videos and 20 hours of lecture. For module 1, generally on any other YouTube platform, you can find just around 8 to 10 hours of recording for module 1. Whereas here we have recorded 50 hours of recording. For module 2, maximum 6 to 8 hours of recording will be there. Already we got 20 hours of recording and 10 more hours of recording I'll try to do. Already 20 hours of content is already available. 10 more hours of content we'll try to accomplish in this month. Module 3 is transmission lines, which we need to start. Module 4 is about waveguides. Module 4 is about waveguides. Both I'll start parallel here. Module 5 is about antennas and optical fiber communication. Optical fiber communication, I'll take a separate series here. I will take a separate series for optical fiber communication. Antennas we had covered. Antennas Mahamarathon series, where we created a playlist with 18 videos. We created a playlist with 18 videos and 38 hours of content. So overall we have, in module 1 we have 50 hours of content. In module 2 we have 20 hours of content. In module 5 we have 38 hours of content. Already we are having 108 hours of content here, and I'm ready to deliver 112 more hours of content, which will make exclusively 220 hours of content for EMFT. So what we have done in module 1, let me explain. What we have done in module 1, let me explain here. In module 1, elements of EMF theory. In elements of EMF theory, just common for electrical and ECE. In this, we started with basics. The idea behind starting with basics is most of the students are having problem with the basics of EMF theory. That's the main reason why EMF looks a difficult subject rather, a bit difficult subject rather. So my idea is first to make the basics clear for all the students so that this subject looks very easy. As you know, this playlist is for 40 videos and 50 hours. In this 40 videos and 50 hours of lecture, 15 hours of lecture is on basics. Such strong basics were discussed in this particular module. Please go through this playlist for understanding the module 1 very clearly. So in basics, I divided the basics into two parts. elements of vector calculus, first part, and coordinate system. That's the second part. In part 1, elements of vector calculus, in part 1, elements of vector calculus, we discussed quantities like scalar quantity. What is scalar, dear? Scalar is something which is having only magnitude, no direction, represented by capital letters. Next, we see vector quantity. What is vector, dear? A vector is one which is having both magnitude and direction. Then we have seen unit vector. Unit vector given by AA, AB, AC. Unit vectors along vectors ABC. Unit vector will always give you direction of the vector. Scalar quantities, if you ask me examples, for scalar quantities, examples are like distance, time, speed. For vector quantities, you have force, torque, acceleration. Okay. Now, can anyone tell me, like, what is current? Current is scalar or vector? Current, most of the people think that current is vector quantity. Most of the people think that current is vector quantity, but it is not the case, dear. Current is actually scalar. Despite having magnitude and direction, current is not a vector quantity. It is a scalar quantity, dear. Current is a scalar quantity, it is not a vector quantity. Despite having magnitude and direction, current is a scalar quantity. Why? Why so? Because vector is defined as something which has magnitude and direction and which obeys vector addition. And current is one which does not obey vector addition. That's the reason under special case, current is something which is having magnitude and direction. Still, it is a scalar quantity because every vector must obey vector addition. With this, after this, we have started vector addition. Addition of vectors. Addition of vectors is done by two methods. Parallelogram law and head to tail rule. What is parallelogram law, dear? According to parallelogram law, if A and B are two vectors which are two arms of a parallelogram, then the resultant vector, the diagonal C is equal to A plus B, is the diagonal of the parallelogram. Hope you got this. If A and B are two vectors which are two arms of a parallelogram, the resultant vector C is equal to A plus B is the diagonal of the parallelogram. Similarly, from head to tail rule, if A and B are two vectors such that the head of A joins the tail of B, then the resultant vector C is equal to A plus B, starts at tail of A and ends at head of B. That's head to tail rule. These are two rules through which you can do vector addition, or we can perform addition of vectors. Then we discussed on the basic laws of vectors. What are the basic laws of vectors that you are having here? basic laws of vectors, commutative law, associative law, and distributive law. And we have discussed on commutative law of addition, commutative law of multiplication. Similarly, associative law of addition and multiplication, distributive law of addition and multiplication. Coming to commutative law of addition, if A and B are two vectors, then A plus B is equal to B plus A. Commutative law of addition. If K is a scalar and A is a vector, K into A is equal to A into K. Commutative law of multiplication. Coming to associative law, if A, B, C are three vectors, such that A plus of B plus C is equal to A plus B plus C. This is associative law of addition. If K and L are scalars, K into LA is equal to K into L into A. This is associative law of multiplication. Next is distributive law. K into A plus B is equal to Ka plus Kb. Can anyone tell me what is distributive law of multiplication? Just think, pause the video and think. What is distributive law of multiplication? This is frequently asked interview question here. What is distributive law of multiplication? Something a frequently asked question. This is something which is frequently asked question in your interviews. Actually, the reason is there is no distributive law of multiplication, because the distributive law of addition only we are doing this multiplication. This is regularly asked interview question here. This is also regularly asked interview question. Why current is scalar? If you want to know exactly why current is scalar, please go through the series or the playlist of module 1, where I took a separate class and explained why current is scalar. In short, I can say that current is scalar because it does not obey vector addition. Does not obey vector addition. Then we had seen multiplication of vectors. Then we had seen multiplication of vectors. Yes, dear. Under multiplication of vectors, what you are having? Under multiplication of vectors, we have dot product, or also called as scalar product, and cross product, or also called as vector product. Let us discuss on this. Dot product, also called as scalar product. Can anyone tell me why dot product is called as scalar product here? Why the dot product is called as scalar product? if A and B are two vectors, A dot B mod A mod B cos of theta AB, dot product of any two vectors is a scalar quantity, and that scalar quantity value will be mod A mod B cos theta AB, where theta AB is the small angle between A and B. This is the formula that we use when the angle is given. When the angle is not given, for suppose, given that A is AX plus AY plus AZ B is BXAX plus BYAY plus BZAZ. When angle is not given, the dot product is given by A dot B is equal to AX BX plus AY BY plus AZ BZ. This is when angle is not given. This is when angle is not given, and this is when angle is given. Now you tell me, dear, dot product obeys how many basic laws? Like commutative, associative and distributive. Think and tell me. Dot product obeys how many basic laws? What are the basic laws you have? Commutative law. Tell me whether dot product obeys commutative law, dear. If dot product obeys commutative law, then A dot B is equal to B dot A. Verify once. Is A dot B equal to B dot A? Absolutely. This is A dot B, which is equivalent to B dot A. As A dot B is equal to B dot A, it obeys commutative law. Dot product obeys commutative law. Next. Associative law. Tell me, dear, does dot product obey associative law? Associative law. Order should not change. A dot B dot C is equal to A dot B dot C. Tell me, dear, is it possible? Is it possible to write it in this way? Not possible, because B is a vector, C is a vector, dot product of these two vectors is one more vector. This B is a vector, C is a vector, this dot product of these two vectors is a scalar, and A is one more vector here. So a vector A is a vector and B dot C is a scalar. You cannot do dot product between a scalar and a vector. Therefore, writing itself is not possible. Therefore, dot product does not obey associative law. Next is distributive. Distributive law. A dot B plus C is A dot B plus A dot C, implies dot product obeys distributive law. Implies dot product obeys distributive law. Next is cross product. Are also called as vector product. If A and B are two vectors, then A cross B is equal to mod A mod B sin theta AB into AN. Mod A mod B sin theta AB represents magnitude, AN represents the direction. This is the formula when angle is given and theta AB is the small angle between A and B, where theta AB is the small angle between A and B. If angle is not given that A is AX plus AY plus AZ, B is BX plus BY plus BZ, then A cross B is equal to determinant of AX, AY, coefficients of first vector capital X, capital AY, capital AZ, coefficients of second vector BX, BY, BZ. This is when angle is not given. This is when angle is not given. Now you tell me, dear, cross product obeys how many basic laws? Cross product obeys how many basic laws? Does it obey commutative law? Anyone? Does it obey commutative law? Yes, dear. Please tell me. Does it obey commutative law? Does it obey commutative law? Yes, dear. It does not obey commutative law. It is anti-commutative. That means what? A cross B is not equal to B cross A. It is anti-commutative. But rather A cross B is equal to minus B cross A. You can verify. Or also it is minus of B cross A. This is from the property of determinant. Please go to the playlist here for detailed analysis of this. So this is commutative law, and these both are same. Remember, from the property of determinant, minus B cross A or B cross of minus A is equal to minus of B cross A. Property of determinant: if a scalar quantity is multiplied to any one of the element of a cross product, that scalar quantity can be taken common. Clear? So it is not commutative, it is anti-commutative. Next. Associative. Whether it is associative here, A cross of B, A cross B cross C is equal to A cross B cross C. Is it associative? First tell me one thing, dear. Can we write this? Because in dot product we are not able to write. Dot product of two vectors got a scalar and a scalar and dot. Scalar cannot be done dot product with a vector. So there the operation was not possible. But here B is a vector, C is a vector, cross product of two vectors is one more vector. We can easily do the cross product with that. It is not absurd. But the bigger question here is, are they equal? They are not equal. Please verify. It is not associative. It is not associative. Next is distributive. A cross of B plus C is equal to A cross B plus A cross C. A cross B plus A cross C, it is distributive. It is not commutative, it is not associative, but it is distributive. This we have studied in multiples, the multiplication of vectors, dot product and cross product. And in this first section of elements of vector calculus, studied about vector identities and also del and its del and its operators. Seventh one, we had also learned quantity del and its properties. Del and its properties. These properties are also very, very important here. Del represents the reverse of delta. Is given by dou by dou x of ay plus dou by dou y of ay plus dou by dou z of az in Cartesian coordinate system. Del is also called as vector differential operator. Vector differential operator. Del is called as vector differential operator or spatial derivative operator. Or spatial derivative operator. Del is called vector differential operator because it is doing differentiation and also it is internally a vector. Therefore, it is called vector differential operator. It is called as spatial derivative operator because we are trying to do derivative with respect to space coordinates. And del is a very special operator here. Del, when operated on a vector using a dot product, this is read as divergence of A. This is read as divergence of A. Divergence of any vector is a scalar quantity. This we have discussed. And del when operated on a vector using cross product is called curl of A, which is a vector quantity. When del operated directly on a scalar, it is called gradient of scalar, which again is a vector quantity. We have seen del dot A now. When this del dot A is equal to 0, then A is said to be divergence-less. Del dot A is not equal to 0. It has definite divergence. Or when del dot A is positive, then A is treated as source. Del dot A is negative, then A is treated as sink. Clear? Everyone, is it clear? No. Coming to curl. Del cross A is curl of A. If this curl is 0, rotation is 0, A is said to be irrotational. A is said to be irrotational, cannot be rotated. If they are not equal to 0, A is rotational. Gradient del of V, gradient of any scalar is a vector quantity. Clear? This topic we have discussed. Del and its properties. Eighth one. are vector identities. Vector identities are nothing but the rules followed by all the vectors. First one, divergence of curl of any vector is 0. Second, curl of gradient of any scalar is 0. These are the two main vector identities one must note down. In the second part of the basics, we had seen coordinate system. Coordinates very simple, x, y, z coordinates. Therefore, the limit is also very simple. In coordinate system, we learnt Cartesian coordinate system, cylindrical coordinate system, and spherical coordinate system. In Cartesian coordinate system, coordinates are x, y, z. Cylindrical, they are rho phi z. Spherical, it is r theta phi. Okay. Coming to these coordinates, x is the shortest distance on x-axis, or x is the distance on x-axis parallel to x-axis, or shortest distance from yz plane, limit minus infinity to plus infinity. The limit for y same as x, minus infinity to plus infinity. Limit of z minus infinity to plus infinity. Similarly, in cylindrical coordinate system, the range is 0 to infinity, rho, radius of cylinder, phi azimuthal angle 0 to 2 pi, z is height of cylinder, 0 to infinity, height cannot be negative. Next is spherical coordinate system. Spherical coordinate system, r theta phi. R is the radius given by 0 to infinity. Theta is quadrant angle by 0 to pi. Phi is azimuthal angle given by 0 to 2 pi. And also we have seen point transformation. See about point transformation. How to convert a point from one coordinate system to another coordinate system. That is point transformation. It's in unit vector relations. That is how Ax, Ay, Az, A rho, A phi, Az and Ar, A theta, A phi are interrelated. Very good topic, that is unit vector relations. We have seen differential length, surface and volume in all the three coordinate systems. Then we derive divergence, curl and gradient, divergence, curl and gradient in all the three coordinate systems. These were the basics. Then we have started elements of EMF theory. In elements of EMF theory, we divide into two parts. Static field theory and time varying field theory. Under static field theory, discussed on electrostatics, and magnetostatics. Electrostatics and magnetostatics. Electrostatics is basically study of static charges, and magnetostatics is basically study of charges moving with uniform velocity. What are the basic laws? What are the basic laws that govern electrostatics, dear? What are the basic laws that govern electrostatics, dear? The basic laws that govern electrostatics. Coulomb's law is a generalized law that governs electrostatics. We discussed about Coulomb's law and their applications for line charge, surface charge and volume charge. We've done those derivations and applications, numericals on that, previous year questions and practice questions. Coulomb's law and applications. This is a generalized law that governs electrostatics. Under special cases, we use Gauss law. For usage of Gauss law, we need to define a Gaussian surface. And a Gaussian surface is one which is symmetric with respect to charge distribution. For example, you have a point charge. For a point charge, the Gaussian surface is a sphere. For a line charge, the Gaussian surface is a cylinder. Got it? So in this way, whenever you have these Gaussian surfaces, we can apply Gauss law. Similarly, the generalized laws that govern magnetostatics. The general law is Biot-Savart law and its applications. Special law is Ampere's law. And we can apply Ampere's law only when we define Amperian path. We can define Ampere's law only when we define Amperian path. An Amperian path is something which is symmetric with respect to current distribution. So in this electrostatics and magnetostatics put together, we have derived Maxwell equations for static fields. Maxwell equations for static fields. Maxwell first equation, closed surface integral of d dot ds is equal to volume integral of rho v dv. Differential form del dot d is equal to rho v. Source Gauss law for electrostatics. Second equation, closed loop integral of E dot dl is 0. Differential form del cross E is 0 implies static electric field is conservative, irrotational, because its rotation is getting 0. This is called conservative nature of electric field. Third mantra, closed loop integral of h dot dl is equal to surface integral of j dot ds. Integral form, differential form, del cross h is equal to j. Source Ampere's law. Fourth one, closed surface integral of b dot ds is 0. Differential form, del dot b is equal to 0. This is from non-existence of magnetic monopole, also called as Gauss law for magnetic fields. These are basically we have derived these derivations, which are Maxwell equations for static fields. Clear? Yeah. These Maxwell equations are very important here. Complete subject actually revolves around these equations. Got it, everyone? One second here. One second. Pardon me, 1 second. One second. Just one moment here. Okay. Sorry, dear. Sorry. Fine. Sorry, all. Maxwell equations for static fields. Okay. So let us see how they are derived it. Maxwell first equation is from Gauss law. According to Gauss law, amount of flux cut by any closed surface is equal to the charge enclosed by the surface. This is called Gauss law in true form. This is called Gauss law in true form. Psi is equal to charge enclosed. Psi, where D is electric flux density given by electric flux per unit surface area. If you consider a small surface area, ds, the flux associated is d psi, given in coulomb per meter square. From this you get d psi, or d psi e is d into ds. This is called scalar notation. In vector notation, d psi e is d dot ds. From this, psi e is equal to surface integral of d dot ds. We got psi e. surface integral of d dot ds. Charge enclosed. Charges can be like you can have point charge at a given point. It can be positive charge or negative charge, plus q or minus q. Line charge, charge in a given line. If this line is having a charge q and that charge is distributed throughout the line, total charge is q, total length of the line is L, then this line is supposed to have uniform line charge density rho L. It is total charge by total length, units coulomb per meter. If you consider a small length dl in it, the charge associated with it is dq. Give it as dq by dl. From this dq is equal to rho L dl. Q is line integral of rho L dl. That's the relation between the distributed charge density rho L and the total charge q. Similarly, if you consider a surface, having surface area S, carrying uniform surface charge density rho S, total charge distributed is q, then rho S surface charge density is total charge by total surface area, unit coulomb per meter square. If you consider a small surface area from which this is ds, from which the charge associated is dq, then you can write this as dq by ds. From this dq is rho S ds, q is surface integral of rho S ds. Similarly, when you consider a volume V carrying uniform volume charge density rho V, carrying charge q, total charge q, then this volume is supposed to have volume charge density. It's total charge by total volume. If you take a small volume dV, charge associated is dq. Therefore, dq is equal to rho V dV. Q is volume integral of rho V dV. So from this we can write Q is related to distributed charges as Q is line integral of rho L dl, surface integral of rho S ds, and volume integral of rho V dV. This is generalized case. So we take volume integral. Therefore we got closed surface integral of d dot ds is equal to volume integral of rho V dV. This is called the integral form of Maxwell first equation. Integral form of Maxwell first equation. Okay? Good. Now, if you apply divergence on LHS, what is divergence theorem, dear? Divergence theorem is closed surface integral of A dot ds is equal to volume integral of del dot A dv. It gives a definite relation between closed surface and volume. For example, A is any energy source, just like a light source. The amount of light that is kept on the closed surface is equal to the amount of light that is spreading, diverging or spreading in the volume. See how beautifully closed surfaces and volumes are interrelated by divergence theorem. Applying such divergence theorem on this LHS, applying divergence theorem, closed surface integral of d dot ds is equal to volume integral of del dot d dv is equal to volume integral of rho v dv. From this we get del dot d is equal to rho v. This is called differential form of Maxwell first equation. Maxwell first equation, that is how we are derived. Second equation we are derived from conservative property of electric field. Electric potential V is related to E as V is equal to minus integral of E dot dl, where L is the length. If we consider this length to have 2 points A and B, the potential difference between these 2 points VAB is equal to VA minus VB, which is minus integral of B to A E dot dl. Now you see VAB is equal to VA minus VB. If we extend this up to C, now you get what? VAC. What is VAC? VAC is VA minus VC. Extend it, you get VAD. VA minus VAD is VA minus VD. Now extend it up to A. VA minus VA, 0. Implies whenever you close this loop, the value of potential will become 0. 0 is equal to minus closed loop integral of E dot dl. Implies closed loop integral of E dot dl is equal to 0. It's called the integral form of Maxwell's second equation. Integral form of Maxwell's second equation. Okay. So these two equations are for static fields, okay? Now, next is Ampere's law. Next is Ampere's law. According to statement of Ampere's law, circulation of magnetic field intensity, closed loop integral of H dot dl is equal to the current enclosed by the loop. How current and current density are related? Current density J is equal to I by S, unit ampere per meter square. If you consider a small surface area ds, current associated with it is di, J is di by ds. From this we get di is equal to J into ds. I is surface integral of or you try to write it in the vector form. di is equal to j dot ds. From this I is equal to surface integral of j dot ds. This is when you are operating on open surface. When you operate on closed surface, closed surface integral of j dot ds is I. This for closed surface. Now tell me dear, shall I take open surface or closed surface here? Here you are having closed loop. Closed loop can maximum enclose open surfaces only. Therefore closed loop integral of h dot dl. Circulation of h is equal to surface integral of j dot ds. This is called the integral form of Maxwell third equation. Integral form of Maxwell third equation. Applying Stokes theorem on this. What is Stokes theorem dear? Closed loop integral of a dot dl is equal to surface integral of del cross a dot ds. Applying Stokes on it, closed loop integral of h dot dl is equal to surface integral of del cross h dot ds is equal to RHS, surface integral of j dot ds. Equating on both sides, del cross h is equal to j implies static magnetic field is not conservative. So what's the conclusion? Static electric field is conservative but not static magnetic field. Static electric field will move in straight lines. The static magnetic field will not move in straight line. They form curved path across the conductor or across a straight current carrying conductor. So true. The third one, fourth one, non-existence of magnetic monopole. Non-existence of magnetic monopole, also called as Gauss law for magnetic fields. Non-existence of magnetic monopole means what? As the name indicates, a magnetic monopole does not exist. In a magnet always we have two poles, north pole and south pole. Even if you break the magnet, it will again form north poles and south poles. Monopole cannot exist. And outside the magnetic flux lines will move from north pole to south pole. Inside the magnet, outside the magnet moving from north pole to south pole. Inside the magnet, they move from south pole to north pole, forming closed loops, the uniform magnetic flux. So can anyone tell me what is the net magnetic flux here? This fellow is giving psi m and consuming psi m. So what is the net flux here? The net flux is 0. The net flux is 0. We know relation between magnetic flux and flux density. Magnetic flux is closed surface integral of B dot ds. Given here net flux psi m is 0. So we get closed surface integral of B dot ds is 0. Applying divergence. Del dot B is equal to 0. Static magnetic field is divergence-less field. B is a divergence-less field. It is a solenoidal field. Its divergence is 0. Its divergence is 0. Got it? These are these four equations. Other than this, in static field theory, we have derived about Poisson's and Laplace equations. In Poisson's and Laplace also, dear, we have done some wonderful problems on Poisson's and Laplace equations. Some very good problems we have done, dear. Please go through. Everyone, please go through the playlist. You can find a unique approach. Probably you can't find anywhere. A unique approach for Poisson's and Laplace equation and detailed solution. Very much useful for engineering services. Chances for asking in engineering services is really very high. So that we have done along with numericals. And also we had solved boundary conditions. What are boundary conditions, dear? In boundary conditions we have dielectric boundary conditions and dielectric conductor boundary conditions. And dielectric conductor boundary conditions. For dielectric boundary conditions, we got the boundary conditions as ED1 is equal to ET2. Tangential component of electric field is continuous across the boundary of discontinuity. It is unconditionally continuous. For the derivation, please refer the marathon series, dear. Similarly, dN1 is equal to dN2, provided if and only if rho s is 0, where rho s is the surface charge that is deliberately placed on the boundary. This is conditionally continuous. The normal component of electric flux density is continuous across the boundary of discontinuity if and only if rho s is equal to 0. Done. Vector notation. ST2 minus ST1 is equal to K cross AN. K cross AN. Vector notation. Scalar ST1 is equal to ST2 if and only if K is equal to 0. Tangential component of magnetic field intensity is continuous across the boundary of discontinuity if and only if K is 0. Next, unconditionally continuous. Bn1 is equal to Bn2. The normal component of magnetic flux density is continuous across the boundary of discontinuity. When you take conductor or perfect conductor, as you know, no field can exist between a perfect conductor. These boundary conditions will change as E tan is equal to 0. Tangential component of electric field on the surface of perfect conductor is 0. D normal is equal to rho s. Normal component of electric flux density will be equal to surface charge density. H tan is equal to K cross AN. B normal is equal to 0. These are dielectric perfect conductor boundary condition. One more very important topic. both gate and ESC. Other than this, we also completed capacitors and inductors, types of capacitors, types of inductors. We have parallel plate capacitor, coaxial cable capacitor, spherical capacitor, and also we derived the derivations for parallel plate capacitor. We got capacitance epsilon A by D. For parallel plate capacitor, coaxial cable, we got 2 pi epsilon L by Ln of B by A. A is the radius of the inner cable of the coaxial cable, and B is the radius of the outer cable. For spherical capacitor, capacitance is 4 pi epsilon by 1 by A minus 1 by B, where A is again the radius of the inner conductor, and B is the radius of the outer conductor. This is what we have discussed in static field theory. Yes. This is what we discussed in static field theory. Then we went for time varying field theory. In time varying field theory, it mainly derived two derivations. One is Faraday's law. According to Faraday's law, the induced EMF within any closed path is equal to rate of change of flux linkage. Later on, Professor Heinrich Friedrich Emil Lenz, he said that the induced EMF will always oppose the flux produced rate, and they have kept a negative sign here. Given a negative sign here, where flux linkage lambda here is n times of psi m. VEMF is equal to minus n times of d psi m by dt. For straight conductor, n is 1. VEMF is equal to minus d psi m by dt. Psi m is surface integral of B dot ds. VEMF is integral of E dot dl. VEMF is equal to closed loop integral of E dot dl is equal to minus dou by dou t of surface integral of B dot ds. Closed loop integral of E dot dl is surface integral of minus dou b by dou t dot ds. Applying Stokes on LHS, surface integral of del cross E dot ds, surface integral of minus dou b by dou t dot ds. Removing the surface integral, del cross E is equal to minus dou b by dou t. This is Maxwell equation based in Faraday's law. We will insert in time varying fields. Before we go for Maxwell contribution, let me explain you conservative property of charge. According to conservative property of charge, the rate of decrease of charge the rate of decrease of charge within a closed volume is equal to net outgoing current. Current is related to current density as we derived in the previous slide. I is equal to closed surface integral of J dot ds. We discussed this here, am I right? Here. And Q in also we have discussed. Volume integral of rho v dv. Minus d by dt volume integral of rho v dv is equal to closed surface integral of J dot ds. Closed surface integral of J dot ds is volume integral of minus dou rho v by dou t of dv. Applying divergence theorem, closed surface integral of J dot ds is volume integral of del dot j dv is volume integral of minus dou rho v by dou t of dv, implies del dot j is equal to minus dou rho v by dou t. This is called continuity equation. So, continuity equation is also called as continuity equation for currents. So, from continuity equation del dot j is equal to minus dou rho v by dou t. Now, let us see Maxwell contribution. What is Maxwell contribution? What is inconsistency of Ampere's law? As we want to prove inconsistency of Ampere's law, I am considering Ampere's law. From Ampere's law, del cross H is equal to J. If you take divergence on both sides, del cross H is equal to del dot J. What happens to LHS here? What happens to LHS? According to vector identity, divergence of curl of any vector is 0. So you will get a 0 there. Del dot j is 0. But from continuity equation, del dot j is minus dou rho v by dou t. This is the ambiguity. In order to overcome this, what Maxwell has done is he has slightly modified this equation. He has added a term called displacement current density, a current that can fly in air. A current that can fly in air. What he had done? He had done divergence on both sides. Divergence of curl of any vector 0. You got 0 here. Del dot j plus del dot jd. From this we get del dot jd is equal to minus del dot j. And from continuity equation, del dot j is minus dou rho v by dou t. Minus dou rho v by dou t. Minus of minus, this will become plus del dot jd is dou rho v by dou t. From Gauss law, del dot d is equal to rho v. Del dot jv is equal to dou by dou t of del dot d. Del dot jd is del dot dou d by dou t. From this we derive jd is dou d by dou t. jd is dou d by dou t. Therefore, from the equation, del cross H is equal to J plus jd. J is conduction current density, depends on conductivity of the material, given by sigma E. JD is displacement current density, depends on time varying electric field, or depends on time varying quantity. This is the new equation here. So for time varying fields, now if you try to drop Maxwell equations, for time varying fields. First equation, closed surface integral of d dot ds is equal to volume integral of rho v dv. Integral form, differential form, del dot d is rho v. Source, Gauss law for electric fields. Second equation, closed loop integral of E dot dl is equal to surface integral of minus dou b by dou t dot ds. Applying Stokes theorem on LHS, del cross E is equal to minus dou b by dou t. This is from Faraday's law. And very clearly there is a interlink between these two equations if you see carefully. Orientation of electric field, or I can say spatial orientation of electric field, depends on time varying magnetic field. There must be dependency between these two quantities if these two quantities are to be part of a wave. Exactly the same is happening. Closed loop integral of h dot dl is equal to surface integral of j plus jd dot ds. Differential form, del cross h is equal to j plus jd. J is conduction current density, sigma E. JD is displacement current density. This is from Maxwell Contribution. Also called as inconsistency of Ampere's law. Fourth one, closed surface integral of B dot ds is 0. Implies del dot B is 0. Gauss law for magnetic fields. Also called as non-existence of magnetic monopole. These are Maxwell equations for time varying fields here. And if you observe these two equations, you can find some typical thing in these two equations. Del cross E is minus dou B by dou T. Del cross H is J plus JD. If you observe these two equations carefully, spatial orientation of electric field depends on time varying magnetic field. Spatial orientation of magnetic field depends on time varying electric field. Now that very clearly there is a dependency between this spatial variation and time variation. That's why this can be part of a wave. Now because wave is something which varies its phase with respect to space and time. Exactly that is what is happening here. There is interdependency here. So if you club these two equations, you will get wave equation, or also called as Helmholtz equation. del square E is equal to gamma square E. Del square H is equal to gamma square H. These are Helmholtz equations. Solving this, you will get expression for E and H. Is that clear? So what is a wave, dear? A wave is something which changes its phase with respect to space and time. If you take a wave, wavelength here is 0. It is lambda. Lambda is the distance travelled by the wave to complete one cycle. Half lambda by 2, lambda by 4, 3 lambda by 4. Wavelength. Time 0, t by 4, t by 2, 3t by 4 and t. Phase shift 0, pi by 2, pi, 3 pi by 2 and 2 pi. And a wave is one which changes its phase with respect to both space and time. A wave is one which changes its phase with respect to space and time. The time variation is given by omega t. Omega t will give you the time variation. Beta x, the wave is propagating in x direction. Beta y, it is propagating in y direction. Beta z, propagating in z direction, gives you spatial variation. How omega t will give you time variation? Omega, time period is 2 pi by omega. Omega is 2 pi by t. Change of phase with respect to time. 2 pi radian, time second, radian per second. Let us see omega t. When t is equal to 0, omega t 0. So it implies t is 0, phase shift is 0. T is t by 4, omega t 2 pi by t into t by 4, pi by 2, t is t by 4, phase shift is pi by 2, t is t by 2, omega t 2 pi by t into d by 2 pi, t is t by 2, phase shift is pi. What does it imply? It implies that then you can also verify the rest. Omega t, what it is showing you? The change of phase with respect to time. Similarly, beta x, beta y and beta z will show you the change of phase with respect to space. Got it? So omega t is giving you the change of phase with respect to time. Now let us see how beta x, beta y and beta z will give you the change of phase with respect to space. We need to see now.